In this measurement, we will deal with the loss of fluid energy due to internal friction. As we already know, the cause of it is viscosity. In the case of turbulent flow, the roughness of the inner wall of the pipe also contributes to the losses. Our task will be to determine the coefficient of friction lambda and to compare the obtained values with theoretical assumptions. We will first get acquainted with the composition of the entire hydraulic circuit. The source of the liquid is a tank with a volume of 40 liters. Water is pumped into the hydraulic circuit by a Weberman circulation pump type 2560180, the output of which can be regulated in 3 stages, 55, 70, and 100 watts. Behind the pump is a discharge pipe on which an orifice is located. We can use the orifice to measure the flow. The pressure is taken in front of and behind the orifice. Based on the pressure loss determined from the difference in level heights in the connected piezometric tubes, the volume flow value is deducted from the calibration curve of the orifice. The hydraulic circuit contains 4 measured pipe sections of the same length and of different internal diameters. From above, 18, 14.4, 23.2, and 18 millimeters. Each section is equipped with a ball valve at the inlet, which can lose the flow through a specific branch. We take pressure samples at the beginning and the end of individual sections, and the distance between tapping points in all cases is 1 meter. The pressure points are connected by polyethylene hoses with piezometric tubes. The pressure drop is measured by using the pressure heights in the connected piezometric tubes. From the difference in the levels of both tubes, we determine the loss height. This can be further converted to pressure loss using the relationship for hydrostatic pressure. Water flow is regulated by means of a ball valve of the waste branch of the circuit, which opens back into the tank. We will show the principle of measuring the pressure loss using the example of a pipe with an internal diameter of 23.2 millimeters. We will check the connection of the pressure taps to the piezometric tubes using hoses. We will also check for the connection of the pressure taps on the orifice. We will open the ball valve for the measured section of the pipeline and leave the other valves closed for the others. We will turn on the pump and set the appropriate speed. At the beginning of the measurement, we completely open the control ball valve on the waste branch of the pipeline and perform the first measurement for maximal flow. We subtract the difference in level heights in the piezometric tubes connected to the delta HC orifice and to the pressure taps in the delta H pipe. We will write both values, delta HC and delta H, into a pre-prepared chart. We will slightly close the valve, let the flow stabilize for a while, and read again the corresponding values of the level difference in the piezometric tubes. We will gradually close the valve and repeat the measurement for about 8 to 10 flow values until it is completely closed. We then repeat the same procedure for pipes with a different internal diameter. After the measurement, we close the control ball valve again. We then turn off the pump. Measurement evaluation. The known variables are the internal diameter, pipe length, and gravity acceleration. The density and kinematic viscosity of water are determined on the basis of laboratory conditions. The measured values are the loss heights on the orifice and on the straight section of a specific pipe. The calculated variables are volume flow, the water velocity in the pipeline, the Reynolds number, pressure drop, and friction coefficient lambda. We subtract the volume flow from the calibration curve of the orifice on the basis of measured height loss, delta HC. Be aware of the units in which the orifice loss and the volume flow are indicated. We determine speed from the continuity equation. In this calculation, it is necessary to substitute the internal pipe diameter. Values are given in the specification of the elements. We next determine the dimensionless Reynolds number. We convert the loss height by friction to a pressure loss. The following relationship applies to the loss height by friction, and hence the coefficient of friction, lambda. The measured piping can be considered hydraulically smooth. Blasius defined the relationship for the friction coefficient depending on the Reynolds number in the form. We construct the dependence of the pressure loss on the volume. Delta P is a function of volume flow. We plot the dependence of pipes with different diameters for comparison. Using regression, we determine the type and coefficient of dependence using XL, the trend line. We depict the calculated values of the friction coefficients lambda, depending on the Reynolds number. In the graph, we compare the values determined from the measurements with the values calculated according to Blasius for all measured sections. We will adjust the graph, state the name of the graph and the labels of the axes, while not forgetting the units of the variables displayed. We will make comments on the measurement results at the end of the recording.